So you hear about AI like ChatGPT all the time, right? But what's actually going on under the hood? Well, today we're going to pull back the curtain on the revolutionary architecture that powers it all, the transformer. We're going to visualize step by step exactly how these incredible models think. But first, let's kick things off with the big puzzle, the central mystery of it all. You see, at its very core, an LLM is really just a superpowered predict the next word machine. So how on earth does that one simple job lead to something that can write poetry, debug code, or explain quantum physics? That's the amazing paradox we're going to unravel today. So let's dive right into that fundamental task. What does it actually mean for an AI to just predict the next word? So when a model sees a sentence like this one, it's not just thinking, okay, what's the single best word to put next? No. Instead, it creates a probability score for every single word it knows. It might think, well, probably has a 20% chance, undoubtedly has a 15% chance, and arguably has a 10% chance. And by kind of dipping into this pool of high probability words, instead of just grabbing the number one choice every single time, you get text that feels, well, creative. It feels natural, not like some clunky robot. Okay, but here's the thing. Computers don't speak English, right? They speak math. So for any of this to work, we first have to translate our language into their world. And this is where the real magic begins, with something called embeddings. So the first thing the model does is chop up the text into little pieces called tokens. You can think of these like Lego bricks for language. They're the basic building blocks the AI works with. Sometimes it's a whole word, sometimes it's just a piece of a word like un, or even just a comma. And then each one of those tokens gets turned into a really, really long list of numbers. We call this a vector, or more poetically, an embedding. And this isn't just some random serial number. Oh no. This vector is carefully crafted to capture the actual meaning of that token. Okay, now this is where it gets really cool. These vectors aren't just lists of numbers. They have relationships. Let's walk through a classic example to see exactly what I mean. We'll start with the vector for the word king. Now, what happens if we do a little vector math? Let's take that king vector and subtract the vector from man. What we're left with is, well, it's kind of like the pure essence of royalty, but we've stripped out the maleness part of it. So we have this concept of royalty floating around. Now, let's take that and add the vector for woman. Any guesses what we end up with? Boom! The result is a vector that is incredibly, almost spookily close to the actual vector for the word queen. This is mind-blowing, right? It shows that meaning isn't just a label, it's literally encoded in the geometry of this mathematical space. Concepts like gender and royalty are just directions you can travel. And just to give you a sense of scale, we're not talking about some simple three-dimensional space you can plot on a graph. A model like GPT-3 uses vectors with, get this, over 12,000 dimensions. Just try to wrap your head around that. That's how it can capture all the tiny, subtle nuances of language. All right, so we've got our words turned into these super rich, meaningful vectors. So what happens next? Well, now we send them into the main event, the transformer's processing engine. So here's the big picture, the whole journey from start to finish. We've done step 1, text to tokens. We've done step 2, tokens to embeddings. Now those embeddings get fed through a whole stack of identical processing units called transformer blocks. And after all that processing, the model makes its final prediction for the next token. So inside each of those processing blocks, you've basically got two main departments. First up is the attention block. This is where the vectors all get to talk to each other to figure out the context of this specific sentence. And then there's the MLP block. You can think of this as the model's giant library of facts. It's where it stores all the general knowledge it has learned about the world. Okay, let's zoom in on that attention part, because honestly, this is the secret sauce. The attention mechanism is the revolutionary idea that made transformers so powerful. It's how the words figure out which other words they need to pay attention to. Here's how it works. For every single token, the model creates 3 new special vectors. The first one is called the query. Think of the query like the token raising its hand and asking a question. For example, the token for creature might be asking, hey, are there any adjectives around here that are describing me? All right, next up is the key vector. If the query is the question, the key is like an advertisement for an answer. So the token for fluffy might generate a key that basically shouts, yep, I'm an adjective and I'm right before a noun. I might be what you're looking for. And that brings us to the third piece, the value vector. So when a query from one word finds a matching key from another, it's the value vector that actually contains the goods. It's the information that gets sent over. In our example, it's the very concept of fluffiness that gets packed up and delivered from fluffy over to creature. So the model does this for every single word, calculating a match score between every query and every key. And this creates what we call an attention pattern. And if you look at this grid, you can literally see it happening. Check out how the words fluffy and blue are paying a ton of attention to creature. It's working! They're talking to each other. Okay, so let's just quickly recap that whole dance. For every token, you create a query, key, and value. You calculate attention scores to see how much each word should listen to every other word. You use those scores to create a big blend of all the value vectors. And finally, you add that blended information back to the original token, making it smarter and more context-aware. Now, that whole attention process is a ton of work for the computer, but it has some really special properties that just blew everything else out of the water. So the big question is, why did this specific design take over the entire world of AI? It really boils down to three huge advantages. First, they are massively parallelizable. Unlike older models that read word by word, transformers look at everything at once. This design is tailor-made for the way modern GPUs, the chips that NVIDIA makes, work. It's a match made in heaven. Second, they scale like crazy. You give them more data and more computer power, and they just reliably get better. And third, and maybe most importantly, they're self-supervised. This means you can just dump the entire internet on them and they learn all by themselves. You don't need an army of humans to label data, which is a massive, massive bottleneck. And all this leads to a pretty wild final thought. Remember how we said they process all the words at once, not one by one like us? That means transformers don't experience time or sequence the way we do when we read. They see it all in one instant. So I'll just lead you with this to chew on. What does it actually mean for an intelligence to think outside the flow of time?